Yeah, Mikkel, I'd say go for it.
All right, so we'll probably have people trickle in, but that's all right. They'll just miss me giving a brief introduction to Harpeth, but they'll catch the important parts, which is our guest speakers tonight. But as Ryan said, my name is Mikkel. I'm an AmeriCorps member serving with Harpeth Conservancy. And I'll just give a brief background on Harpeth Conservancy and before we hand it off to Roger and Marina. But we are a science-based conservation organization, and our vision is to provide and promote clean water and healthy ecosystems for the rivers of Tennessee, and importantly, to have that cause be championed by the people who live here. And overall, our goal is that all of the state rivers meet required federal and state water quality standards. And the way in which we do this can be summed up by this acronym with the word rivers. We do restoration projects, we address pollution issues, and then provide a voice for all members of our community in order to find solutions. We also educate our community members, as well as promote responsible recreation, and then do all of the work and fulfillment of our vision through the foundation of science. So our programming and work efforts can be summarized into 4 categories. That is clean water protection, community engagement, science and restoration, and rural protection and land use. So a couple of the programs that kind of implement our vision, one of them is Lessons on the River, and these are hands-on and in person, and we hold them each month. We have a couple coming up that we'd like to invite you to. In June on the 16th, we have pollinators and native plants. We're going to be at Bates Nursery. And this is exciting. It's a continuation of our last month's conservation conversations where we discussed invasive and native species. So this kind of adds to that topic by being in person, learning which species to plant in your garden. There's 2 sessions, so go ahead and sign up through our website for those. And then in July, we have our Family Fun Day. And as you can see, all of these events are possible through our funders and sponsors. Alongside our Lessons on the River, we have conservation conversations, which we are all participating in at the moment. And these, rather than being in person, you get to enjoy these from the comfort of your own home. So we have virtual discussions. We hold them every month, always on the 4th Wednesday, always at 6 p.m. Very reliable. And we cover a range of environmental issues, a range of topics, and we always invite in experts who know more than we do to come talk about it with us. And so coming up throughout the summer, in June, we have Understanding Dams and Their Impacts. July, we'll talk about emerging water quality issues within the state of Tennessee. And then in August, we'll go over the work that Harpeth is doing with water sampling and what we've been able to find so far. So in addition to our programming, there's other ways you can take action. There's volunteer opportunities. You can find us on social media, use the Water Reporter app. You can also get the specialty license plate. A portion of those proceeds do go to our organization. So if you're interested, please visit this website you see on the screen, riverplatetn.org, in order to do that. And finally, the reason why we're all here is to hear from Roger Lindsey and Marina Metes to talk about flooding in Tennessee. So Roger is a program manager with Metro Nashville Water Services, and Marina is a physical scientist with USGS. So we'll first hear from Roger, and then we'll hear from Marina, and then we'll have a chunk of time at the end if you have any questions. Feel free to put them in the chat, hold on to them till the end, or throughout the discussion, and we'll get to them for sure. So I'm going to invite Roger to start sharing his screen, and while he preps his presentation, I'll give you guys a short introduction to him. So Roger graduated from Mississippi State University with a BS in civil engineering and a MS in environmental engineering, and he's a registered in Tennessee and Mississippi, and completed the requirements to become an ASFPM certified floodplain manager. He is the practice leader for stormwater master planning and for floodplain management for Metro Nashville Water Services, serving also as the floodplain administrator for the city of Nashville and Davidson County. He's worked in the water and wastewater industry for over 35 years with experience in environmental regulation, water and wastewater design and construction, and most recently in water resources and stormwater engineering. He's also led permitting efforts for reconstruction of damaged properties following the historic flood that occurred in Nashville on May 1st and 2nd, 2010. Roger is presently serving as the president of the Tennessee Association of Floodplain Managers, as well as the president of the Certification Board of Regents for the Association of State Floodplain Managers, and as chairman of the Franklin Tennessee Planning Commission, chairman of the Franklin Stormwater Appeals Board, and also past president of the Mississippi Water Environment Association, among other organizations. All right, Roger, so you can go ahead and share your screen, and I'll hand it over to you.
Okay. Okay, it was easy to share my screen a few minutes ago. Now I don't. I don't see.
Green button at the bottom.
Green button. Okay.
Yep. Do you see it?
No.
At the bottom of the Zoom window, the green button that says share screen.
Sometimes slips down below.
Okay.
So
Yeah, I never found a green button, but
see share screen.
Might have to move.
Okay.
There you go. You got
Yeah.
it.
There you go.
okay. Okay, so I was given about 4 topics to speak about and 15 minutes to do it in, so I should run over by about 45 minutes. So not really though, I'll talk fast and I won't read every bullet on every screen. I'm not a bullet reader. So I want to talk about flooding in Tennessee, but I also have a bit of an alternate title to my presentation, and it goes something like this. I don't care what you think about climate change. There's something funky going on with the weather. By disclaimer, I am not a climate scientist, but I watch a lot of extreme weather events. I report out to the Emergency Operations Center in Nashville whenever we have an above average kind of an event coming toward Nashville, and there's an activation of the Emergency Management Center. Some others of you may have spent time at EOC during activations. I know Hands on Nashville during a major event usually has a presence in the war room, and so. But we do watch. We watch the weather and we keep a close eye on things, and we make decisions relative to response to severe weather events. So what is a 100-year event? I look at NOAA Atlas 14. It's still called the average recurrence interval expressed in years. And so a 100-year event is as much as 1.5 inches of rain in 15 minutes, or 3 inches in an hour, roughly 5 inches in 6 hours, 7 inches in 24 hours, 12 inches in 10 days. All of those are considered to be 100-year rain events. And you don't want to confuse a 100-year rain event with a 100-year flood event. They're 2 entirely different animals. 100-year rain is an intensity duration kind of a thing. How hard does it rain and how long does that rain last? While a 100-year flood is the same as the 1% flood, is derived from the HEC-RAS model of the stream of the river, specifically from the flood profile. It's the flood profile allows us to pick values at any given point along the creek or the river, looking at as events as low as 2-year events to 10-year events to 100-year events to 500-year events. But we use it to regulate development as well. And in 2010, this is kind of a summary of the 2 days of rainfall. Franklin, you see, had close to 18 inches of rain in 2 days. Antioch about 16, less as you move north. Nashville, the heart of Nashville, 13 and a half, Percy Priest and Old Hickory, 12 and 13 and 14 inches of rain. But the one thing I like to call out on this particular slide is that you see the brighter, whiter areas where the more intense rainfall fell. That rain fell downriver of the two major impoundments that affect the city of Nashville, downriver of J. Percy Priest Dam, downriver of the Old Hickory Lock and Dam. So for those who believe that the Corps of Engineers still caused the flood in Nashville in 2010, take note of the fact that most of the rain that fell on the city didn't fall in an area that was impoundable by those dams. And then you look at the series of other weather events that have occurred since then. Houston, this was the article in the Washington Post, the weekend of Hurricane Harvey. Houston's experiencing its third 500-year flood in 3 years. How is that possible? Ellicott City, Maryland, this was an article that ran in June of 2018. It reports back the second devastating flood since 2016, both 1,000-year events. Cedar Rapids, Iowa, we talked to Cedar Rapids in Nashville. We talked to Cedar Rapids during the midst of our flood because they had just experienced a catastrophic flood 2 years before ours. And we wanted the benefit of their experience in that flood. And just in 2016, they had yet another major river flood, not as extreme as the first one. I think the river crested almost 10 feet below their 2008 event, but it was still a big event. And then the article again from the Washington Post, state of emergency in Louisiana as atmospheric river unloads disastrous rains. And this article mentions that up to 2 feet of rain have fallen in Louisiana, and 3 people have died as historic flood events swamps parts of the South and the Gulf Coast. But it's interesting, though, that we capture this was a blogger, Tom D. Liberto. He refers to these events as a Maya Express, a 4-day rainfall of over 2 feet in Louisiana. And when you look at the observed precipitation, those darker areas in the Monroe and Schwartz and Shreveport area, indicate rain upwards of 20 to 25 inches, staggering amounts of rain. And so then I started looking at other big events. In June of 2008, that was a Cedar Rapids flood. Atlanta in 2009 had 20 inches of rain in 35 hours. May 2010 was our flood. May 2011 was flooding on the Mississippi River and represented the first activation of the Birds Point New Madrid floodway in nearly 75 years. That had only been activated once earlier and shortly in the years following the completion of that flood diversion structure. Colorado Front Range, 2014, Pensacola, Florida had 22 inches of rain in 24 hours, including 5 inches in 1 hour. March of 2016, that was that severe flooding again in Louisiana and Texas, 14 inches of rain in 24 hours. Houston, both in April and May, extreme events, 12 inches, 16 and a half inches. In June of 2016, Oklahoma had a 9-inch rain event one morning. White Sulphur Springs, West Virginia, 10 inches of rain in 12 to 18 hours with 23 fatalities. And then again, that Ellicott City event in August, Louisiana, the southern half of Louisiana flooded. 25 inches of rain in 3 days. So the flood in March happened in the spring, big event, 2 feet of rain. In August, it happened again, 60,000 homes with water damage. August, 9 to 11 inch rain in San Antonio. And then in October, Hurricane Matthew. And that was a category 5 hurricane with $10 billion in damages and 40 fatalities. And this kind of continued on. In February of 2017, the near failure of the Oroville Dam, they evacuated 188,000 residents downstream of the dam. May of 2017 was more severe flooding. Missouri River, Arkansas River, 15 inches of rain, nearly $2 billion in damages. And then in the fall and late summer and fall, hurricanes Harvey, Irma, and Maria. So So I want to talk a little bit about atmospheric rivers because I mentioned it with that North Louisiana flood. I met Dr. Talbot, who works at ERDIC, Waterways Experiment Station in Vicksburg, at a flood workshop several years ago, and he pointed out to me that the Nashville flood was caused by an atmospheric river, and I had never heard that term before. So this is kind of an example of a West Coast atmospheric river. You see this stream coming, the brightly colored orange and red stream that's coming from well out in the Central Pacific. It's described as a narrow conveyor belt of water vapor extending from thousands of miles out at sea, carrying on average the equivalent flow of about 10 Mississippi rivers. California gets them all the time. That's where 30 to 50% of their annual rainfall comes from. And in the case of this one, 16 inches of rain in one day. This was another exhibit in the material that Dr. Talbot sent me. And you can see another one of those West Coast. But in the middle column here, he had this depiction of the Tennessee flood from 2010. And you can see the angry red and purple colors down in the eastern Pacific Ocean. This event kind of forms over the Central America, the Yucatan Peninsula, and it blows right across the Gulf. And it's doing this at altitude. It's not, it's not a rolling series of cold fronts like we typically get. You can see in that water vapor transport image at the bottom how that flow is coming, and it comes up through Mississippi. And then in the case of our event, it dumped in the middle to western part of Tennessee. Snowmageddon in February of 2010 was an atmospheric river as well. And then he had Dr. Talbot had done a presentation on the Nashville flood, and this was the cover slide for that presentation because it really delved into the physical processes associated with how an atmospheric river dumps and delivers that amount of rain. And in the case of this, you can see that there is a stalled cold front that stretches across Arkansas and Illinois, and it's that cold front when that atmospheric river traveling again at altitude hits that cold front. It just dumped. It just dumped it all in middle and western Tennessee. 44 counties affected by the disaster declaration. There were a couple of other exhibits he gave. Again, this was one that was going on at exactly the same time. This was the March 2016 event that flooded so seriously North Louisiana. And you can see that at the same time that Mayan Express was going on in Southeast Louisiana or North Louisiana, you can see the precipitation forecast from the Weather Service. They were looking at over 10 inches of rain that they were expected. And over those several days, they got way more than 10 inches of rain. There was another one going on, a Pineapple Express that was fed again from the Hawaii area that was inundating the northern California all the way up to Seattle area. So when are they likely to occur? Most often, these are color-coded dots in the southeast. There's a lot less research on the southeast, but more as time goes by. The pink dots really, we think, represent the one that hammered Nashville and areas west. Pink is an event that occurs in the spring. The dark blues are winter events. They're smaller. You can tell that those little circles are smaller in the winter. Gold, again, very small events. Those are summer atmospheric river events. And then the fall, they're light blue and they're bigger, obviously, in the fall as well. And they affect as well North Carolina. And then the little black cross signs on this map are heavy precipitation events in which no atmospheric river was matched. So you can see that they're two very unusual and different kinds of events, those that are not atmospheric river related, and those that are, and typically those that are pretty major events. Famous last words, at least we'll never see another flood like this in my lifetime. That's what we heard after the flood in 2010. So if that's the way you think about it, 100-year event, what do you call these? In August of 2013 in Nashville, there was a significant event that came across the northern part of the city of Nashville. It impacted Whites Creek, Ewing Creek, and all the big trips to Ewing Creek, Dry Creek. That little USGS gauge shows Dry Creek near Edenwald. a hydrograph peak that jumps almost to flood level there. And then the flooding that was taking place right along Briley Parkway. There was a lot of evacuations of automobiles along Briley that were flooded. That was a big event. In Murray County, October of 2015, based on OHSX radar estimates, there's the GM plant, 6 to 8 and then 9 inches of rain that fell in a very localized area close to the GM plant down in Spring Hill. So that was a big event. In August of 2017, we call it the Remnants of Harvey event. And you can see again, we had rainfall totals in Middle Tennessee above the Davidson County area here. There were totals that ranged up from 7 to almost 8 inches. Here's a 9-inch reading. There's a 10-inch, a couple of 10-inch readings as you work your way on up toward the Kentucky line. That's a precipitation event of 6 or more inches of rain. In February of 2019, here we look at the entire month. This was the month of February that was described as one of the most extreme months for rain. And when you see the the color coding on the when you see the color coding, you can see that we're way up at the top end of this scale, above 15 and into 20 inches of rain for the month of February of 2019. And there were record discharges from a number of from Wolf Creek Dam. Wolf Creek Dam was at close to capacity in February of 2019 and had record discharges from the dam. And then just to kind of give you an example of what the Nashville District's storage system looks like, that's Wolf Creek. And these things are sized on this exhibit by scale. So Wolf Creek is the largest of the flood control structures on the Cumberland River. It's bigger than almost all the rest of them put together. The others, including one thing that's interesting is the old Hickory Dam. There's no flood control component to that dam. It's a navigation structure with hydropower and some conservation, but it's kind of a run of the river type of structure. It wasn't built to control floodwater, and so in Nashville we don't look at it as being that type structure. And then last fall, in September of 2020, there was another big event. This one seriously impacted the Mill Creek area. As you can see in the middle of the screen there, the dark red right here at the junction of Williamson County and Davidson County. That's the heart of the Mill Creek drainage basin, and that's a rain event of upwards of 8 inches of rain. And then the next exhibit shows you again one of those radar. This is Mill Creek again. This is the same storm. We're seeing 8 1/4 inches of rain, upwards 8 inches of rain, all that along the heart of Mill Creek. And I drove through that area the morning after that event, and there were cars washed off the road on Antioch Pike, and the water had been obviously well out of its banks. It reminded me a lot of what I saw in that area after the 2010 event in Mill Creek. Mill Creek's a large drainage basin that can be a killer creek. So, and then after our event in March, within a couple of days, because of my relationship with Dr. Talbot at URDIC, he got his guys out in the Center for Western Weather and Water Extremes. The guys on California did a quick analysis of the flooding in Tennessee for that event. And this just shows it was considered to be a stage 4 24-hour event. Again, when you look at the graph, the scale, we've got extreme measures of rain over that 2-day event. And we had, for the other exhibit, in the Nashville area, we're seeing purples over here. We're well up above, we're at in excess of 200 to almost 300% of our normal monthly rainfall that occurred during that month. The Duck River was well into major flood level. the Cumberland River at downtown, that's typically the Nashville gauge, as we refer to it. It was up into minor flood stage at about a 40-foot gauge height. And consider that the 2010 event, the gauge topped out at 52 feet. So we stopped about 12 feet short of where the Cumberland River was in the May 2010 event. And then they were able to classify that the March event was also caused by an atmospheric river. And they compared that event back. This was the same kind of computer simulation that describes what was going on during the May 2010 flood event. It was a bigger event. When you look at the comparison, the March 2021 event had a more robust aggregation of water vapor in what's being described as a developing atmospheric river. So anyway, that's my quick blurb on extreme weather events. One of the things that Dory and I talked about was the use of higher regulatory standards when we regulate, when we do flood recovery. We look at higher regulatory standards. One of the most predominant and the one that we're probably most known for is our freeboard requirement. And that's building the first floor of a building or reconstructing a damaged building above the FEMA minimum standard. So FEMA will let you build at base flood. We required that you build 4 feet above base flood. Franklin has a requirement to build 3 feet above base flood. So research work, Dr. Camp, Janie Camp at Vanderbilt, they concluded that Nashville, because we've had a 4-foot freeboard requirement dating back over 40 years, that we realized in excess of $2 billion of damages avoided in the 2010 flood because all of our structures, our residential structures built since 1979 have been built at a 4-foot freeboard. Other higher standards, access, making sure that primary roadways into neighborhoods are above base flood elevation. We require that you compensate storage. If you fill to build in the floodplain, you've got to excavate material on the same site to offset one cubic yard per 1 cubic yard. Other regulatory standards, we don't have this in place yet in Nashville, but the protection of critical facilities, hospitals, fire stations, anything related to anything considered to be a critical facility in a city, a higher standard would be to build those facilities perhaps to the 500-year event, the 0.2% chance flood, or even to the flood of record. And that's one of the things I think that Opryland did after the 2010 flood was as they rebuilt their flood walls around the Opryland Hotel and their flood protection around the Grand Ole Opry, they built 2 feet above the flood of record. So they're fairly well protected there. Cumulative substantial damage and substantial improvement. In Nashville, we track for a 10-year period. Every improvement that takes place in a structure tallies up to meet that 50% level. If you're above 50%, you've got to bring a non-compliant structure into compliance. The prohibitions against water level rises. Many of you have heard the description of the term. You got to do a no-rise study, and that's what that relates to. Future conditions, hydrologic mapping. One of the things we'll do as we move forward is to model based on full build out to give us a better sense of the impact on our streams for our flood modeling. And then use restrictions. We don't allow you to build a residential property in the floodway here. And we have a number of other restrictions that are described. So right now, we're in the midst of flood recovery. We're working with a number of property owners in the Mill Creek and 7 Mile Creek, McCrory Creek areas. They all suffered very severe, substantial damage, likely worse than the 2010 levels and at those parts of the creek system. We're doing a lot of permitting for repair and construction. To those that are curious, if you suffered flood damage, you need to come to the Development Services Group and pull a permit for that work. And that all goes toward the determination of substantial damage. We need to know how much damage you sustained in the flood event. Ramping up home buyouts, we've got another 150 houses on our list. We've already bought and demolished 400 houses. Those are 400 houses that will never flood again. Again, here now, we're already involved with a Corps of Engineers project, a buyout program in Mill Creek and 7 Mile Creek, and that program will be expanded. And then we continue to upgrade our flood insurance rate maps. We've got 2 more packages of maps, 50 map panels that are close to being ready to release as effective maps, and another 18 panels that we're just now rolling out as preliminary maps. So we continue to upgrade and enhance our mapping system. And then we're also working with Department of Homeland Security to add some stream monitoring gauges that we'll use in conjunction with the USGS gauges that are part of our flood forecasting system, our Nashville Safe system. So with that, I ran long, but I'm sorry. And so I can do a few questions, or I know we're going to do a good question and answer session at the end. So I will cede the floor.
Yeah, we'll go ahead and do questions at the end.
Yep. Okay.
If anyone has any, feel free to put them in the chat to save them. And Marina, go ahead and set up your screen share, and I will give you all a introduction to Marina. So Marina Metes is a physical scientist with the U.S. Geological Survey at the Maryland, Delaware, DC Water Science Center. Marina's work focuses on using GIS and spatial analysis to answer questions related to hydrology and fluvial geomorphology. Her research involves using remotely sensed data, primarily LiDAR, to map and investigate fluvial geomorphic features, processes, and land use change. This has included developing new methods for locating headwater streams and incised channels, and developing geospatial tools to extract stream and floodplain characteristics at the watershed scale to improve estimates of stream bank erosion and floodplain sediment deposition. Marina received a BS in Earth Science from Michigan State University in 2012 and an MS in Geography and Environmental Systems from University of Maryland, Baltimore in 2018. And from 2012 to 2013, she served as an AmeriCorps member with Harpeth. So welcome back for the evening, and take it away.
All right, great. Thank you for having me. So my talk will be slightly different. I'm going to be focusing on floodplain ecology and geomorphology, and particularly in the portion of the floodplain that floods fairly frequently. And so yeah, I'll get started. I just want to start by just acknowledging some of my collaborators and my coworkers who have been heavily involved in a lot of the work that I'm going to show. And then I just wanted to acknowledge the funding sources that made this work possible. And then just kind of a quick overview of what I'll be going over. I'm just going to talk about the physical and ecological floodplain processes that occur during floods, and then how we measure these in the field, and then how we can use this information along with other remotely sensed data, so data that's kind of collected not right at the site, and modeling to look at this information on a large watershed scale and at areas that we aren't able to measure in the field. And so just to kind of get started with this overview of what a floodplain ecosystem looks like. So floodplains are dynamic landscapes. You can see in this cross section that there's lots of different landscape features that are supported within floodplains. And there's also just some specific animals and plants that are supported in floodplains. And so this is what this kind of looks like in reality. You can see on the image on the right, this was taken pretty long after there was actually a rain event, but there's still a lot of standing water in the floodplain. And then this image on the left was actually taken, Roger had mentioned the Ellicott City, Maryland flooding. So that's actually right near my house. And this was taken shortly after that flooding occurred. So the flooding in Ellicott City was on a pretty small tributary that runs into a much larger river. And so this was the floodplain in that larger river. And so the the river that feeds into, or the river that flooded in Ellicott City feeds into a larger river that is surrounded by a big park area. And so, you know, there's just a much larger floodplain that was able to support that flood water. And so, you know, luckily there was not a lot of damage downstream from that area because there was this wide floodplain that was able to kind of capture all of that flood water. And you can really see all the vegetation has been pushed into the direction of the water that was flowing. And all of this sediment was probably about a foot thick of sediment that had been deposited on the floodplain. And so I guess what is sort of obvious from these pictures is that floodplains store a lot of water and sediment, but they also have a lot of other benefits where they can slow down the flow of floodwaters when they are vegetated. And so, you know, just like in here, you can see that the water was flowing pretty quickly, but also this vegetation was slowing down the velocity of the river. And so that also helps with erosion control downstream and retention of floodwaters. And then with those floodwaters, you have a lot of sediment and nutrients that are deposited onto the floodplain. And so especially when those sediments and nutrients are deposited on a floodplain and stick around for a long time, those can kind of be considered what are called like sediment and nutrient sinks, because it removes those sediments and nutrients from downstream environments. And then you also have more groundwater that's being recharged. And so the plant species that are supported in floodplains are able to kind of thrive and provide wildlife habitat. And then in areas where we do have floodplains that are preserved, a lot of times there's public parks that might be present as well. And so that also provides an opportunity for recreation. And so just going more into detail about why we care about sediment and nutrients and why it is really beneficial when they can be stored in floodplains. So nutrients like nitrogen and phosphorus are found in various sources across the landscape, especially in urban and agricultural areas. And so when it rains, they run off into nearby rivers. And too many nutrients in a river can cause problems like excessive algae growth. And so that can lead to lower oxygen in the water, which can be fatal to aquatic species. There's even toxic algae that can be really harmful to humans and pets. And sediment as well, just sediment alone when in excess can also disrupt habitat in streams. And then a lot of times nutrients like phosphorus and other contaminants like to attach onto sediment particles. And so, you know, we wanted to know how much sediment and nutrients are actually stored in floodplains. And so this specific work that I'm going to be talking about occurred in the Chesapeake Bay and the Delaware River watershed. But we essentially went to 68 areas and measured sediment and nutrient dynamics. And so these sites kind of spanned a range of geography. You can see we have some sites kind of over here in the Blue Ridge Mountains that do extend down into Tennessee. We have areas in the coastal plain, which is a lot flatter, which would kind of be similar to places in Western Tennessee. And so at each of these sites, the way that we measured how much sediment is eroded from the stream banks or deposited on the floodplains was through this approach called Dendrogeomorphology. And so which is basically a way to use trees as a tool to measure the rates of sediment deposition and bank erosion. And so the word stems from dendrochronology, which refers to tree ring dating. So what we did was we sampled 10 trees along the floodplain and 10 tree roots along the stream banks. And so what we can do is we can core the tree to find the age of the tree. And then we find the amount of sediment that's deposited over what's called the basal root. So I don't know if you can see my mouse, but it's kind of this root that extends laterally across the floodplain. And it grows this way when the tree is first established. And so we can assume that any sediment that's kind of sitting on top of that root was deposited after the tree was established. And so if we can get the age of the tree and the amount of sediment that's been deposited over that root, we can divide the depth of the sediment by the age of the tree and get an annual rate of sediment deposition at this particular site. And then for stream bank erosion, we cut out cross sections of exposed tree roots. And so similarly, we use the age of the tree root, and then also to, so we look at the tree root, and usually when it's been exposed to air or water, there will be some sort of indication in the tree root. And so if we can identify that point at which the root was exposed to air or water, we can, measure how many years since that point this root has been exposed. And then we can also measure the distance between that root and the stream bank to come up with an estimate of the annual bank retreat or bank erosion. And so we do this for each of our field sites, and we can then average out those two values to see if sites are more erosional or depositional. We also take this sediment back to the lab and measure for different chemical makeup of the sediment. Like we look for carbon, nitrogen, phosphorus, and then just the mass of the sediment. So we can also kind of know how much sediment is eroding or depositing on these floodplains. So these are just the results of the amount of sediment and at all of our different sites. And so positive values would be sediment that is deposited, and and the negative values are sediment that's been eroded. And then the blue bars on this graph show the floodplain values, and the red bars show the stream bank values. And so then this little like yellow diamond kind of shows the net amount of sediment. And so in areas where it's less than 0, this is a site that's eroding more than the sediment is depositing on the floodplains. And in areas where it's higher than 0 is where there's more sediment that's being deposited. And we have our results categorized in these 5 different regions, which actually the Appalachian Plateau, the Blue Ridge, the Valley and Ridge, and the Coastal Plain all cover most of Tennessee. I think the only portion of Tennessee that's in a different physiographic region is kind of in Middle Tennessee. But I guess these sites were in the Chesapeake Bay, but you could sort of expect similar patterns across these different regions in Tennessee as well. And in the mountainous regions, we don't really have much of anything going on just because we have smaller floodplains. A lot of times we just have a lot of smaller streams. And then, places like the Valley and Ridge, where you have sort of like rolling hills and then some flatter valleys, you have really a mix of both net sediment erosion and deposition. And then in places like the Coastal Plain, which also cover Western Tennessee, you have much higher rates of sediment deposition. And so this is just a flatter area where, we do have broader floodplains and flatter topography. And then this is just showing the same results, but with nitrogen. And so it has a similar pattern as the sediment. And I guess I just wanted to highlight this one with nitrogen too, because it really shows in a lot of these sites, more nitrogen is being stored on the floodplain than is being eroded along the stream banks. And so that's also really important because in places where you're using like a river for drinking water, this is actually a really beneficial thing because it's removing this nitrogen from the river system. And so it might actually reduce costs of nitrogen removal at drinking water treatment plants. And so this is what is called an ecosystem service. That is just one thing that floodplains can help to do. And so the next question is, can we look at these patterns at sites that we haven't measured? And the answer is yes, we can do this with other data that is available across the entire watershed, and then we can combine that with models. And so the data that we use that I mentioned earlier that's collected remotely is called LIDAR, which stands for light detection and ranging. And it's usually collected from an airplane, and it sends off a laser pulse, which will reflect off of multiple surfaces. And so it will reflect off things like the tree canopy, so you can look at vegetation structure, but it also reaches through the vegetation to the ground. And so you can get a really detailed ground surface. And so we use that to better map out things like floodplains and streams. And so this is just where it's available, which it does cover the entire state of Tennessee. And I think these slides are going to be available later. And so I have a link if anyone wants to kind of learn more and download any of the data and see more specific details, like the years that they're collected varies and the accuracy varies as well. But this just shows you what it actually looks like. So you can see the really detailed stream network, and then this blue area is the floodplain that we extracted. And so just looking at the imagery, you just see, trees, and then you see the floodplain. And so it's really a helpful tool to be able to pull out floodplain information. And so I won't go into any detail on this, but again, there's a link if you want more information. But we developed a tool that we can use to pull out floodplains. And so, it's all open source code, but if you have any other specific questions related to it, then I would be happy to answer those later. But what it does is it pulls out stream bank information, like bank height. And so just at two different scales, we have kind of this local scale where we have stream bank information spaced every 9 meters across the stream. And so you can see really detailed patterns of how the stream bank gets a lot steeper and deeper as we go into this urban area, which is a pattern that we typically see and would expect. And then you can kind of look at changes across an entire watershed. And what, with this topic being on flooding, what you're probably more interested in is the floodplain characteristics that we can pull out. And so we estimate flooding extent at various depth intervals using our LIDAR surface. And so what this animation is showing is just at different depths above the water surface, the areas that would be flooded. And this isn't a perfect model. This isn't nearly as, doesn't go into nearly as many details as something like a HACRAS model that's used for flood mapping for like insurance and regulatory purposes. But it does give us a good idea of where the floodplain is located for our work. And so we also calibrated this with field measurements in that we collected in the field, and combined it with other information like the size of the watershed and the different region that we were in. And so what we kind of were able to do across the Chesapeake Bay watershed was model the entire watershed to look at areas where we have higher rates of both bank erosion and floodplain sediment deposition. And so this is a really helpful tool for looking at areas that are prone to erosion or sediment deposition on the floodplain. And so it can be especially useful for people who are looking to maybe target areas that are in need of stream restoration or floodplain restoration. Or what I think is really important for flood mitigation is finding areas that are maybe could be more successful for floodplain conservation or floodplain restoration work, to kind of select areas that would be good areas to either conserve or kind of expand the floodplain to kind of make room for floodwaters so that you mitigate that flooding further downstream. And kind of just to bring it back to Tennessee, since this is where most people probably except me are located. Another thing we can do with LIDAR is if we have repeat LIDAR that's measured at 2 different periods in time, we can difference the elevation of the 2 data sets to look at actual change that has happened over time. And so I just pulled this out. This is an area along the Harpeth River that's just south of Highway 70. And there was LIDAR available for 2011 and 2018. And so the red areas are negative values. And so this is showing erosion that's occurred over time. And then the blue areas are showing sediment deposition. So I don't really know any more about this site. I don't know if there's been any sort of construction or other sort of kind of human-induced changes, but this is a really useful way to look at actual change that has occurred, or maybe look at areas that, maybe this is an area that floods fairly frequently because we are seeing a lot of change between these 2 time periods. And unfortunately, I couldn't find any LIDAR for previous to the May 2010 flood, because I think that would be really interesting to be able to look at some of these larger scale changes that may have happened before and after that flood. And, I guess until we get updated LIDAR, we can compare the 2018 data set to anything that's newer that's been collected. But I just wanted to highlight this as another really useful tool to look at changes that have happened over time. And so that I will also be happy to take any questions, and there's my contact information. I also added just my office website for USGS, and then also the Lower Mississippi Gulf Water Science Center is the office that covers work specifically in Tennessee. So I included their website as well, and they actually have a local office in Nashville. So thank you.
Thanks, Marina and Roger. We have about 5 minutes for questions. If we don't get to everything, we'll be able to, take note of them and send them out and have our guest speakers answer them, and then have a follow-up email for all of you with their responses. So we'll, start at the top and see how far we get. So first we have, I guess this is for Roger. In your opinion, what should we be categorizing or measuring rain events that would be helpful for citizens, scientists, home buyers, etc.?
Of course, the HEC-RAS model defines what the flood event levels are, the 2-year, 10-year, 100-year, 500-year. But I had information just today from some of the guys that I work with at the Corps of Engineers. Franklin had some fairly significant